Hey guys, welcome to chapter 17. We are going to dive into our chapter on kinetics. For this exam will cover just the kinetics chapter. So we'll have two modules for those of you that are taking my hybrid or online. We'll have two modules for this chapter. So the first module will cover 17.1 to 17.3. And then the second module will cover 17.4 to the end. So what is chemical kinetics? Chemical kinetics is the study of how things change over time. Okay? So how fast are these reactions happening? How slow are these reactions happening? So what is going on over the course of time? Kinetics also sheds some light on reaction mechanism. So one of the most vital pieces of knowledge that chemists would like is how reactions happen. What is the mechanism of this reaction? So with chemical kinetics, we can start to kind of shine a light on that and then also piece together what this reaction is, what it is doing and how it's occurring. So that's the last thing, is it's going to give us a better picture of how this reaction occurs and not just it's occurring, that's it. So when we talk about kinetics, there's kind of two categories that we're going to talk about. The first one is average reaction rates, and then the second half is like instantaneous reaction rates. I'm going to spend this video and maybe one more talking about average reaction rates, and then the rest of the module and into the next one will be more like instantaneous. So just a disclaimer here, don't sleep on average reaction rates. You will see a couple questions on the test. So average reaction rates is the measure of how a reaction changes over a given amount of time. We're used to these average rates. We've used them every day without really thinking about them. So one example of average rates would be like speed. So miles traveled over an hour's time, miles per hour, okay? Another one that you might often see is like weight gain or weight loss. So how is my weight changing over 3 months, 6 months, a year? So those are just a couple examples of average rates that we talk about without thinking much about it. So when we talk about the average reaction rate, the bottom of this equation is going to be the same. So some given amount of time. It could be seconds, it could be minutes, it could be days, it could be years, but some given amount of time. And then on the top, we're going to monitor the change in concentration. So for the last two chapters, we've been talking about concentration. That is one thing that holds true for this chapter as well, is we're still monitoring the concentration of our equations. Okay. So the average rate of a reaction is going to be the change in concentration divided by the change in time. The way that we symbolically represent this, so this triangle symbol is delta. It denotes change. So anytime you see that triangle, just read it as change. So we've got change in concentration. That's what the brackets mean, and they mean concentration. So change in concentration of hydrogen divided by change in time. You see this kind of magical minus sign that appeared when I wrote this. So let's talk just quickly about this reactants and products. So we're back to one-sided arrows. So everything's going from left to right. Okay. So during a chemical reaction that's one-sided, reactants always go down. We use those up. Products always go up. We always make them. So that's where you see this subtraction sign, because if I'm monitoring the change in the reactant, it's going to be a negative value. If this was just HI, that would be a positive value. So the other thing that we have to consider is the stoichiometry of this, okay? So during this chemical reaction, one molecule of hydrogen reacts with one molecule of iodine. That's pretty easy, right? But we also have to consider the fact that we're making two molecules of the product, okay? So when we're writing these equations, we want one rate equation for the entire reaction. Or another way of saying this is we want our rate per mole, right? We don't want to know how fast we can make 2 moles. We want to know how fast can we make 1 mole. So as we're getting used to writing these rate equations, we also need to address this 2 in front of the product, because we want to take the rate per mole. So if I were to write the rate for the product, here's what it would look like. Okay. So this is the average rate of the reaction. On the bottom is going to go change in time. Okay, so we're looking at it over a given amount of time. I'm writing the rate for the product, so that's going to be a positive value. And on the top, we're going to write change in concentration of that product. Now, the last thing that we have to address is this 2. So the way that it's written now, we're looking at the rate of making 2 moles of the hydroiodic acid. I want to know what is the rate per 1 mole. So I am going to divide by that coefficient. By dividing by that coefficient, that's going to give me the rate of the formation of 1 mole, not 2. So anytime there's a coefficient, we always put 1 over that coefficient to give us the average reaction rate. So this was kind of an example of, for this particular problem, here's your kind of generic formula for writing the average reaction rate. So here we have A reacts with B to produce C and D. These little a, little b would be the coefficients. This may be a 2, this could be a 4. And so the rate is going to be the change in time. On the bottom, change in concentration on the top. 1 over the coefficient for each of these. And then notice my reactants have a negative, my products have a positive. Okay? So just kind of the generic. One of the things I do like about this graphic in this formula is we notice this is a single rate for the whole reaction. So I could look at the rate of the consumption of A, I could look at the rate of formation of D, but all of those equal the same value, which is why we have to address the coefficients. So let's look at an example. If you want to try it on your own, go ahead and pause the video, and then I'll catch up to you. But I want to write the rate for each of these different molecules. So for the reactant, for the product, and for the other product. So give it a shot and I'll catch up to you. All right, so we're going to first talk about the rate of the reactant. So rate equals, that's how we're going to start all of these. Change in concentration of our reactant divided by change in time. It is reactant, so I'm going to put that negative sign in there. And then we also have a coefficient to take into account. So I'm going to put a 1/2 at the beginning. Now I want to do the same thing for my products. So rate equals change in concentration of NO2 divided by change in time. This is a product, so we're forming it. That's going to be a positive. And this one also has a coefficient, so I'm going to multiply by 1 over that coefficient, 1/4. And then lastly, the rate of O2. So we're going to have change in concentration over change in time. It is a product, so it's going to be a positive. And there's no coefficient, or there's an implied 1. So if it makes sense in your brain to put 1/1, that would be fine. But in this case, we don't really need that coefficient. So that's writing the rate expression for each of the molecules. And remember, this is an average rate of reaction. In the next video, we will quantify this. So we'll start looking at some data, and we will put some numbers to this. I hope you guys found this helpful.